Welcome back. Today we're proving the fundamental theorem of calculus for complex path integrals. So we have the statement over here, but I want to remind you that because real integrals are a special case of complex path integrals, we're also proving the fundamental theorem of calculus for real integrals. We're not going to be using the fundamental theorem of calculus for the real case. The purpose of this organization of the material is so that we can prove everything all at once. So we're proving calculus, we're proving the fundamental theorem for the real case, and we're also proving it for the complex case in one go. So that's the agenda here. Let's look carefully at the statement. So this is for complex path integrals. We have a path gamma. It's assumed to be continuous and bounded variation. We have a function f. I'd like to say that f maps from the complex numbers to the complex numbers, but we don't need f to be defined on all complex numbers. In fact, if f of z is a function like 1 over z, then it won't be defined for all complex numbers. We need it to be defined on the image of gamma. And so it may be defined certainly more than that, but at least it needs to be defined on the image of gamma. And we're going to assume that it has a primitive f. That just means an antiderivative, a function cap f whose derivative is that. And we're also assuming that little f is continuous. Notice that that means that cap f is continuously differentiable, which is going to be relevant because we're going to use theorems that we know that apply to continuously differentiable functions. We're going to use theorems like this on cap f. Then what's the theorem statement? The theorem statement is it's easy to calculate the derivative. The derivative on the path gamma of f of z dz is cap f of gamma of b minus cap f of gamma of a. You might have expected cap f of b minus cap f of a. Let me point out what's going on here. So if we have a path in the complex plane, so the beginning point and the ending point of the path, the complex numbers which begin and end the path, will not be a and b, but will be gamma of a and gamma of b. So basically, think of the path as a two-dimensional domain of integration as a one-dimensional domain of integration within the two-dimensional complex plane with a beginning point and an ending point. But those beginning and ending points are gamma of a and gamma of b. Then you evaluate the primitive cap f at the end point and the beginning point in this sense, not at b and a. This may be a little bit surprising because we've talked an awful lot about Riemann-Stieltjes integrals. And then now you notice that's not a Riemann-Stieltjes integral, that's a path integral. So that might cause you some concern. If you're concerned about that, don't be too concerned because it is, of course, also a Riemann-Stieltjes integral. It's the Riemann-Stieltjes integral of the function f composed gamma d gamma from a to b. So that is a kind of Riemann-Stieltjes integral, but it's not the Riemann-Stieltjes integral of the function f, it's the Riemann-Stieltjes integral of the composition f with gamma. If you're real interested in real variable calculus and you're interested in a real fundamental theorem of calculus, this proof goes through, the proof that we'll give here, and this theorem too, go through when gamma is simply the identity function on the interval ab. So if gamma maps ab to AB, which is a perfectly legitimate path, if that's the identity function, then this path integral works out to be the integral from a to b of f of x dx. So if your real interest is in real variable calculus, then you can get the real variable version of the fundamental theorem of calculus by just letting gamma be this trivial path. So that's the sense in which this integral here, which is a path integral, is related to the Riemann-Stieltjes stuff that we've done before and is related to the normal real variable calculus that you're probably used to. So we need to prove that this thing is, that this integral is equal to this. Now, I'm going to start with a step which is not strictly speaking necessary in the proof. I'm going to just prove that this integral exists. Actually, we will calculate its value, and in calculating its value establishes that it exists. But I want to point out here that if we interpret this as a Riemann-Stieltjes integral of f composed with gamma d gamma, then we already have a theorem that tells us that an integral will exist, a Riemann-Stieltjes integral will exist, provided that the relevant path is bounded variation and the relevant function is continuous. So gamma is assumed bounded variation here, and f composed with gamma is continuous because f is assumed continuous and so is gamma. And so this thing exists by the prior work. But we don't actually need to perform this step. We don't need to prove that it exists because we're going to directly calculate it as a limit. So the goal is to show that the limit which defines this integral is equal to this. So what I'm going to do is I'm going to take this integral as a Riemann-Stieltjes integral, and I'm going to open it up in terms of the limit of partitions, and then I'm going to assert that that's equal to that. So the goal here is to show that the limit as partition norm goes to 0 of the summation I equals 1 to m of f of gamma of tau I. Now tau depends on p, and so does t. And then so that's f composed with gamma here on the inside of the Riemann-Stieltjes integral, and then d gamma, so gamma of ti minus gamma of ti minus 1. We want to show that this limit is equal to cap f of gamma of b minus cap f of gamma of a. So that's the goal. We need to show that this limit is equal to that value. Now, how do we show that the limit is equal to the value? We're going to take an arbitrary partition, and we're going to try to control the difference between this and this. So, what we're going to consider is the error in the estimate by a partition, and then we're going to try to prove that that error can be made to go to 0. But before we consider that error, we should do a nice beginning for any proof and analysis. We're going to let epsilon be greater than 0. Epsilon will be a value which we're trying to use to control the difference between this thing and that thing. So we're going to consider the absolute difference between this partition estimate and the thing that I'm claiming that it should have in its limit. So that's going to be the summation I equals 1 to m of f of gamma of tau I minus, times gamma of ti minus gamma of ti minus 1 minus the quantity f of gamma of b minus f of gamma of a. And I'm not going to distribute that minus sign because it would be counterproductive. And then end absolute and modulus sign. So we want to show that this is less than epsilon. So we're trying to show that the limit of this is equal to that. So we need to calculate the difference. We need to show that the difference is less than epsilon. Under what conditions? So long as the partition norm is small enough. In other words, I'm trying to show that there exists a delta, so that if the partition norm is less than delta, then this thing, this error, will be less than epsilon. Okay, so what we're going to do is we're going to try to simplify this expression here. Now, the first thing you notice here, this part is a sum and this part is not a sum. And that means that they're difficult to combine. But the partition of AB, so if I'm trying to draw a picture of P here, T1, T2, T3, etc., this will be Tm, and this will be, of course, T0. The partition of P determines all of these points Ti. And now we've got f of gamma of b, that's Tm, and then minus f of gamma of a is T0. This difference is not a sum. This is a sum. In order to combine them, it would be convenient if this were a sum. This is the difference of two values of the function f composed with gamma here and here. So if we want to open it up as a sum, we can make it a sum of differences. We can take the value here minus here, and then the value here minus here, and the value here minus here, and we can just add up all those differences. If we add up all those differences, then all the intermediate terms will cancel, and we will get this. So we're going to open up this simple difference into a sum of small differences so that we can combine the sums. So this is an equality here. So equals, the first term will not change, but I'd like to copy it down precisely. So we'll get gamma of ti minus gamma ti minus 1. Okay, so that's the first term. And then we're going to subtract a sum of differences. That's the sum I equals 1 to m of f of gamma of ti minus f of gamma of ti minus 1. And then, of course, these individual differences are supposed to be modeled by or approximately equal to these individual terms like this. So let's now combine the sums and see what happens. So this is, again, an equation. So I equals 1 to m of, now we get f of gamma of tau I times gamma of ti minus gamma of ti minus 1 minus cap f of gamma ti minus cap f of gamma of ti minus 1. So this is now inside the sum, but I'm not going to add extra parentheses to show it. Oh, and I need to parenthesize this difference because the whole difference is subtracted. Now, just in case this is like making your head spin, I want to point out that these terms actually have some meaning here. If we think of cap f as like a position or something, and little f as the derivative of it, so a velocity, this is like a difference between two time values times a velocity, and then this is like the difference between two displacements that corresponds to that. So there's some reason to believe that this might be close to that. Of course, that's not precise reasoning. What we want to do here is we want to say basically each of these for each I is going to be approximately equal to these. And so we want to get some sort of hard control that says this minus this is going to be small. But notice that the modulus sign is on the outside. So what I want to do is I want to control each term separately. So I'll use the triangle inequality to move the modulus sign inside. And I'm not doing anything else in this step, but I'll just move the modulus sign inside. And then we're going to have to do something a little bit more algebraically interesting. Okay, so that's the triangle inequality there, and I've moved the modulus sign inside, and I want to control this term. Now, let me tidy this up a bit. So what we're going to do next is we're going to divide. So notice that gamma ti minus 1 is a factor here. What we're going to do is we're going to factor it out. We're also going to factor it out of this term for which it is not a multiple, and that's going to require dividing this term by gamma ti minus 1. So we're going to take this term, basically think of it as we're going to multiply and divide this term by gamma ti minus 1, and then we're going to factor it out. So let's see how that goes, and then let's talk about whether it actually works. So there is actually something we should worry about here, but we'll get to it in a minute. So here I'm simply going to have f of gamma of tau I, and then this term will get factored out, and then this term needs to be divided by that term. So that's going to be f of gamma of ti minus f of gamma of ti minus 1 divided by gamma ti minus gamma ti minus 1. And now this term that I factor out will become a multiple of this whole thing. But when it is, I can also factor it all the way outside the modulus sign and put it in its own modulus sign, basically splitting the modulus of the product into the product of the moduli here. So then we get this. So basically this term, gamma ti minus 1, has been factored out completely. And we've split this up so that the modulus of the product is the product of the moduli. So, so that's sensible algebra, right? I multiply and divide by something, and then I factor it out. The reason for this, so before we get to there's a little problem here, but before we get to it, the reason for this is because I'm angling for this formula. I want this to be a comparison between something that looks like a difference quotient and something that looks like a derivative. And remember that little f is the derivative of cap f. So this really does look like the derivative of what's going on for the difference quotient here. So I'm looking at this formula and I'm going to try to use it. Now there is actually a small potential problem here, and that is if this is 0, then I can certainly factor it out. I'm still multiplying this by 0. But if this is 0, then I can't multiply and divide by it, and I can't put it in the denominator here. So if this is 0, then there is a problem algebraically with what I've done with this term, because I multiplied it and divided by 0 in order to factor out 0 and place a 0 in the denominator. So for a given I value, it could be 0. It's not possible that ti equals ti plus 1, or ti minus 1, rather. For example, it's not possible that t3 and t2 are the same. But the path gamma, as it meanders through the complex plane, might cross itself, certainly. And so this could be, for example, we could have gamma of t1 here, and then here, the next time we reach this point, that would be gamma of t2, and then we could continue, and then that could also be gamma of t3. Because gamma is not necessarily injective, it could cross itself, and so two different points in the partition could go here. Now, it may be unlikely, but certainly it's possible. So we need to be concerned about what happens when gamma of ti minus gamma of ti minus 1 is actually equal to 0. So it is actually a real problem with what I've done here. So let's think about what happens to each term in this sum when gamma ti is minus gamma ti minus 1 is equal to 0. So if that were to happen, let's go back to this sum. If that were to happen, then this term here would be 0, and it would multiply this, and so this entire term here would be 0. What would happen here if gamma, well, if the only way this can be 0 is if gamma ti and gamma ti minus 1 are equal. This has cap f of gamma ti, and this has cap f of gamma ti minus 1. If indeed they're equal, then cap f of 1 equals cap f of another, and so this term here, with the cap f's that is subtracted, this term would also be 0. So the case that we're worried about, where this thing equals 0, is a case when this is equal to 0 and gamma ti equals gamma ti minus 1, and therefore this term is also equal to 0, and so the whole summand is going to be 0. So the terms that we're worried about are terms for which the summand itself is completely equal to 0. That means we don't have to worry about these terms, but we do have to carefully exclude them. So here what I'm going to do is I'm going to exclude them by adding the condition gamma of ti is not equal to gamma of ti minus 1. I'm just going to say that that's a condition on this sum. Now, ultimately, that changes the sum. I mean, it changes the indexing of the sum, but it doesn't change the result. So I can freely add this, right? It doesn't change the result of the sum, so it doesn't interfere with any of these equalities or less than or equal to's, and so we don't have to worry about it. I don't want to rewrite this condition 100 times, so I'm going to put a star here, and then I'm going to just continue to place a star underneath these sums, indicating some terms have been removed, but they were 0 anyway, so don't worry about it. So those terms do not appear here, so sort of by definition of the star, I'm never dividing by 0 here. So, okay, now we're kind of set up for this kind of position here. We've got difference quotients, and we've got a derivative, but we're not exactly equal to this because instead of having w's and z's here, we have gamma. What are we going to do with gamma here? Well, we're going to consider this to be basically, this is like what's happening here, but precomposed with gamma. And so we're going to try to control it like we would control a composition. So if you look up if you remind yourself how to prove that the composition of two functions is continuous, for example, that's a lot like what we're doing here. We're using one term to control the outer function, which is like this derivative minus difference quotient business, and another little trick to control the inner function, which is the gamma itself. So let's continue and make that explicit. What we want now is some sort of strong control over this. Now, what I'm going to do, though, is I'm going to invoke this. So, so let's call this, well, I'll just use an arrow. So, so by this thing, by that result, we're going to choose a row. I'm going to choose a delta. This says for every epsilon there exists a delta. So I'm going to choose the delta that is guaranteed to exist here, but I'm not going to call it delta. I'm going to call it rho because I have in mind something else that we're going to do later, and I need to reserve the name, the symbol delta for that later thing. So we're going to choose a rho, but it's the delta guaranteed here for epsilon, which is that epsilon given there, and the function cap f, which maps the image of gamma onto C. Now, notice here that this function cap f is assumed continuous. It's actually assumed continuously differentiable, which is exactly what we need, right? So the little f in this theorem is going to be played, the role of little f is going to be played by this cap f, which is assumed differentiable, and it's assumed that its derivative is continuous, so it's assumed continuously differentiable. Image of gamma is compact here. This is compact for two reasons. Well, for a combination of reasons, because gamma maps A, B to C is continuous. So if gamma is a continuous function and its domain is compact, a closed interval, then its image will be compact. And so this is a compact domain satisfying this property. This is a continuously differentiable function satisfying this requirement, and we have an epsilon greater than 0. And so we're going to choose a rho. And then what do we know about the rho. So that means for any z naught in the image of gamma, and for any w not equal to z in the ball around z naught of radius rho now, then what do we know? We know that I should use cap f. So we know that cap f of w minus cap f of z over w minus z minus cap f prime of z naught has modulus less than epsilon. So that's what we get by the invocation of this. But here we have w's and z's, and here we have gammas. And we also have the condition here that w is not equal to z, and it has to be within a distance of rho from z naught. So we need to somehow guarantee that that condition is true for all of these gamma ti's and compared to the gamma ti minus 1s. How do we do that? Well, we use the fact that gamma is continuous on a compact set, and so it's uniformly continuous. And so, we're gonna invoke the uniform continuity of gamma. So by the uniform continuity of gamma, which is continuous on a compact set, so it's uniformly continuous. So we're going to choose a delta for, you know what? I think I made a mistake. So I'm choosing rho for epsilon, but I actually need significantly more control over this than it simply be less than epsilon, because I'm going to end up with a variation of gamma in here too. So actually, I made a small mistake here. This should be epsilon over the variation of gamma, which is presumed finite. And then this is going to be less than epsilon over the variation of gamma. Sorry about that. Okay, so now we're going to choose, what are we doing now? We're trying to control these gamma ti's and gamma ti minus 1s. We're going to choose a delta for, I guess, rho, so that if s minus t is less than delta, then gamma s minus gamma t is going to be less than rho. This is possible by the uniform continuity, and that means that if indeed we can guarantee that the inputs of gamma are close enough together, then we will be able to conclude that the corresponding outputs of gamma are as close as we need them to be, so that this actually becomes relevant. Now, how can we guarantee that the inputs of gamma that actually occur in this sum are so very close together? Well, we can use delta to control the norm of the partition P. So I'm going to choose, I'm going to now assume that the partition P has norm less than delta. Technically, this assumption should go right here, but we couldn't have made any sense of it right here. So technically, all of this should happen right here in this proof before we start reasoning about the partition. But you know, it wouldn't have made a lot of sense there. So we're going to assume that the norm of the partition is now less than delta. Now that means then what does that mean about the relationship between the ti's and the tau i's? It means ti minus ti minus 1 is always going to be less than delta. And it means that tau I minus ti, that's always going to be less than delta. And it means that tau I minus ti minus 1, that's going to be less than delta. Basically, when you have a sample point here, tau, this would be tau 2, 3. This would be tau 3. When you have a sample point here, none of the distances between the relevant sample point and the dividing points, none of those distances can be delta or more. So we get all of these things close by. That means that, so when we apply gamma to them, then we get the distance between them less than rho. So gamma of tau I minus gamma of ti, that's going to be less than rho. And furthermore, gamma of tau I minus gamma of ti minus 1 is going to be less than rho. And furthermore, gamma of, we don't actually need this last one, but gamma ti minus gamma ti minus 1, that's also going to be less than rho. All of these things are less than rho, which means that they really are a relevant z0 and w and z in this scenario here, right? That is, gamma tau I is an element of the image of gamma, and gamma ti and gamma ti minus 1 are in the rho ball centered there. And so whatever this asserts for w equals gamma ti, z equals gamma ti minus 1, and z0 equals gamma tau I, whatever this asserts is true. So we can conclude here that, where shall I put this? So we can conclude that the this thing, well, actually, let's just continue there with the inequality. We can conclude that this thing is less than the level of control that we got on it here. So that means that we can continue this proof. And what we get here is a less than, and then we get a summation. And then this thing gets to be controlled to be less than that bound we put on it, epsilon over the variation of gamma. And then, of course, we have gamma ti minus gamma ti minus 1. Notice that this is a little bit tricky here. This condition w not being equal to z is necessary here so that this difference quotient is defined. And it is guaranteed by this condition star that I decided to impose. This is basically equivalent to w is not equal to z for this value of w and this value of z. So now that I've bounded this uniformly for all the I values, it factors out of the sum. So this is equal to epsilon over the variation of gamma times the summation I equals 1 to m of the modulus gamma ti minus gamma ti minus 1. But that's nothing more than the variation of gamma measured with respect to the partition P. So this gives us epsilon over the variation of gamma times the variation of gamma with respect to P. So this is the supremum of things like this. So this variation is less than or equal to that variation. And so that's less than or equal to epsilon, which is what we need. So let's go over this again to make sure that we've done the right thing. So if epsilon is chosen greater than 0, then the right sort of structure of this proof is to skip here immediately. By this fact, we choose the rho so that this works. And then by the uniform continuity of gamma, we choose the delta for gamma so that this equation works. And we take a partition whose norm is less than delta. So in other words, there is a delta so that if the partition is chosen to have norm less than that, then all of this activates. And then we follow this proof through and we get that the difference between that partition's estimate to the integral and the actual claimed value of the integral is less than epsilon. And that's a direct proof by the definition of the limit of the partition function that the limit of this function is equal to this limit. And that shows that the integral is equal to that value. So thus, the Riemann-Stieltjes integral of f circ gamma d gamma from a to b, which is equal to the path integral f of z dz on the path gamma, is equal to its claimed value, f of gamma of b minus f of gamma of a. And that is the fundamental theorem of calculus.